internal routine. For circuit architectures composed of only a few connected devices, such as CMOS inverters or SRAM cells, the steady-state circuit electrical solution can be simply solved considering Kirchhoff's circuit laws and compact models for transistors. In the following, the method is illustrated for the solving of an inverter and a SRAM cell. Figure 5, left, defines the different terminal voltages and the source-to-drain current for the MOS and POS transistors. Figure 5, right, shows the circuit schematic of a SRAM cell consisting of two cross-coupled CMOS inverters. Considering that the particle strikes the off-state MOS transistor termed MOS1, initial conditions V1 equals 0, V2 equals VDD, the time variations of potential V2 for the sole and isolated inverter number 1 can be written as definition of the terminal voltages and the source-to-drain current in N-channel, NMOS, and P-channel, PMOS, transistors, left. Circuit schematic of a SRAM cell formed by two cross-coupled CMOS inverters, right. Reprinted with permission from Otron et al., copyright 2014, Elsevier. Where IT is the current pulse given by 5, due to the particle strike and collected on the node 2, IDN1 and IDP1 are the currents of the MOS1 and POS1 transistors, respectively, and Cn is the node capacitance. Considering this time, the full SRAM cell composed of the two cross-coupled inverters, we obtain the following system of two coupled differential equations. 8, for the sole and isolated inverter number 1 or EX. 8, and 9, for the full SRAM cell can be easily solved in the time domain, using a fourth-order Runge-Kutta method with a time step delta t identical to the one used in the RWDD algorithm for charge transport and collection. Using notations introduced in 8, the incremental results for Tn plus 1 equals Tn plus delta Tr. With EX 10-19, constitute the core model implemented in the code RWDD-CPP for CMOS inverter and SRAM cell solving. In 9, MOS and POS source-to-drain currents are analytically modeled using the EPFL-EKV model 2.6, here implemented in C++ as numerical functions, IDN and IDP, having two arguments, see Figure 5. The EKV 2.6 MOSFET model is a predictive, scalable, compact model for the simulation of submicron CMOS technologies. It was built taking into account fundamental physical characteristics of the MOS structure. The model offers a continuous modeling of the different regimes of the transistor operation, weak, moderate and strong inversion, which is mandatory for circuit modeling. The version 2.6 takes into account numerous essential issues for the transistor modeling such as the effects of the doping profile, substrate effects, process-related aspects, oxide thickness, effective channel length and width and junction depth, mobility effects due to vertical and lateral electric fields, the velocity saturation, short channel effects, etc. Section 5 details several examples of simulations using this code RWDD-CPP.